question belongs to operating system subject and was asked in GATE CSE 1990. It is match the following question. So the question states match the pairs. We have been given two lists, list 1 and list 2. List 1 contains critical region, wait/signal, working set and deadlock. And list 2 contains Hoare monitor, mutual exclusion, principle of locality and circular wait. Let us see all the options one by one. So what is a critical section? So what is a critical section? So critical section is a part of code where we are having the shared resources. So it is part of code where a process is accessing shared resources. So let me give you an example for this. Let us assume we have two programs. Program P1 it has some code over here, then it has read on a variable A, then it has increment on the variable A, and then it has write on variable A. Program P2 starts with read on variable A, it then decrements the variable, and then it will write on variable A, and then it has some operations. So, and A is a shared variable, it is present in the memory. Let us assume it has a value 10. So what happens over here? We can see that A is a shared variable, which means it is a shared resource, and in this part of code P1 is accessing A, and in this part of code P2 is accessing A. So this part of code is called critical section for P2, and this part of code is called critical section for P1. So what happens is that due to this critical section, if both the programs are executing parallelly, then race condition will occur. What is a race condition? Race condition means we will get different output if we have different execution sequences. Let me give you an example for this one. Let us assume we are executing P1 followed by P2. So what happens? First P1 reads A to be 10, then it increments A, which means makes it 11, then it writes A, which means it writes 11 over here. Then when P2 comes, P2 reads A to be 11, then it decrements it to be 10 and then writes over here 10. So we get the output to be 10. But let us suppose we are having a parallel execution. So what happens in parallel execution is, let me clear this stuff out. Yes. So in parallel execution, P1 reads A to be 10. Let us assume now P1 gets preempted and P2 comes in the scene. P2 reads A to be 10. Now P2 decrements 10 to 9 and P2 writes A, which means makes over here 9. Then P1 comes and it increments in its local memory 10 to 11. Then it writes A, which means it writes over here 11. What is the output of parallel execution? P1 parallel to P2, output is 11. So this is race conditioning. It means we are getting different outputs if we have different speed of execution or different sequence of execution. So we need to make sure that at a particular point of time only one program is in this critical section, which can be done, which means we need to ensure mutual exclusion. Thus critical section is related to mutual exclusion. Mutual exclusion means at a particular point of time, to ensure consistency, only one program should be able to access the critical section or access the variable. So critical section is mapped to this mutual exclusion, which means option Q. Now let us see the next option. What is the second option? The second option is wait/signal. So what is wait/signal? Wait and slash are basically commands which, when a process goes on wait state, then wait command is used, and when block state, then wait command is used, and when we want to bring the process back from block state to the working state, then we use the signal command. So first of all, let me tell you what is a monitor. As we have seen just now that we have critical section problem, and critical section problem can be solved by synchronization methods. Synchronization means we need to synchronize which process will enter the critical section. Now what is a monitor? Monitor is basically a high level synchronization construct. So why is it used? It is used to solve the critical section problem. And in monitor, it allowed only safe sharing of abstract data. Their abstract data was A. So it allows safe sharing of the abstract data type A among the concurrent processes P1 and P2. For that example, there can be many processes also P1, P2 up to Pn. Or we can also say that monitor is basically a class like a Java class. A monitor is like a class in which a class will have data as well as functions, in which all the data is private. Private data means no one can access the data from outside the class, in which all the data is private, and with the special restriction that only one method. It will have many methods. It has a restriction that only one method within any given monitor object will be active at a point of time. So only one method can be active at a point of time. Now there is another type of monitor which is called Hoare monitor. Hoare monitor. So what is a Hoare monitor is? So Hoare monitor is basically a monitor with a blocking conditional variable. Blocking condition variables is called a Hoare monitor. And or it is also called Hoare style monitor, or we can say signal and weight monitors. Now let me show you the diagram for this. So this is basically a diagram for a monitor. So you can easily see that monitors can have a weight and signal operations. So weight is used to move a process to the block state, and signal is used to bring it back from the block state. So monitors can be mapped to this weight and signal, Hoare monitor. So B can be mapped to P. Now let us see the third option. So the third option is working set. So what is a working set? So let us suppose we are running a process. So when we are running a process, then a process is divided into page and main memory is divided into frames. So let us suppose we have a process over here, process P1. Process is divided into page, and we have a main memory. Main memory is divided into frames. Now we need, as the process is larger and we may have many processes, we can have a process P22, we can have a process P32, we can have all the process up to Pn. So we need, and they are also divided into pages. So we need to make sure that all the process gets sufficient amount of frames in the main memories. One page can occupy one frame, one page equals to one frame. So we need to make sure that all the processes get sufficient amount of main memory frames. And there are various techniques for this. Like initially we can keep all the frames empty, and then when a request arrives, there will be page fault, and then we can bring the page. But we have a working set algo too for this. Working set algo. So what a working set is, like suppose we are having a program P and we are having some code in it. Let us suppose a loop over here which access some variable. So during this entire execution of the loop, we know only few things will be accessed, like only some variables might be accessed, another variable A might be accessed, this loop variable might be accessed. So they will be present in the closed locality. It might be present that I is present over here, A is present over here. So during this entire loop, only these two pages will be needed. So what is a working set? We can say that working set refers to the pages that are needed by a process at a particular point of time. So we need to bring this entire working set to the main memory, so that if we will bring these two pages, then during the entire execution of the loop, there will be no page fault, as we will have all the required data in the main memory. So what is a working set? Working set is the set of pages which are required at a particular point of time during the execution of a program. And working set algo makes sure that we bring the entire working set to the main memory so as to reduce the page faults. Thus, and you know, working set is based on locality of reference, as the programs that are being, as the pages that are being run at a particular point of time, at that point of time only, the pages which are close to that the current page will only be referred. This is called the locality of reference. So working set is based on locality of reference. So C is related to R. Now let us see the fourth option. The fourth option is deadlock. So what is a deadlock? A deadlock is a condition in which more than one processes are there in the scene and they are not able to execute because each one is waiting for a resource that is held by another process. Let me give you an example. Let us suppose we have three processes, P1, P2 and P3, and we have a resource A with one instance. It is given to process P1, and we have a resource B with one instance which is given to P2. We have a resource C with one instance which is given to P3, and P1 is requesting for B, P2 is requesting for C, and P3 is requesting for A. Here we have multiple processes and they are in block state or waiting state because they are asking for a resource which is being held by another process which is also in the block state. So this is called deadlock. And what are the necessary conditions for deadlock? Necessary conditions for deadlock are mutual exclusion. Mutual exclusion means at a particular point of time, a resource should be held by only one process. Another one is hold and wait. Hold and wait means a process should hold the resource and should wait till it doesn't get its required resources. Third one is circular wait. Circular wait means the process should wait for the resources in circular manner. As here P1 is dependent on P2, P2 is dependent on P3 and P3 is dependent on P1. And fourth one is mutual exclusion, hold and wait, circular wait, and no preemption. No preemption means none of the process should be given the high priority and should be able to preempt another process. So it might not be the case that P3 is having higher priority, so it will be able to preempt P2. We shouldn't allow this. So deadlock has these four necessary conditions. So deadlock is also related to circular wait. So D option can be mapped to S. So the correct mapping is critical map region has been mapped to mutual exclusion, wait and signal has been mapped to horse monitor, working set is mapped to principle of locality, and deadlock is mapped to circular wait.